All right. Hello all. So I'm going to walk through the Unit 2 review. I'm not going to spend a ton of time. I'm not just going to write necessarily everything out because it takes a long time and some of this should be pretty doggone easy. So I'll talk through a good deal of it. So the first one, when we're talking about numbers placed in front of the formulas in an equation, what are they called? So we're talking about, so say something like, if I'm talking about H2O, what about the 3? So the question is, what is this 3 called and what does it represent? So it represents the numbers, the mole ratio or the molecule ratio, right? So we went with a balanced equation. We need to make sure that all of our atoms add up in terms of the law of conservation of matter. And so that 3 is what we're referring to, and it's just called a coefficient, okay? Let's see, moving on to number 2, new substances formed in a chemical reaction are called. You have side A of a chemical reaction is going to create side B of a chemical. These are your reactants. These are your products. Okay, so the reactants react to form the products. Total number of atoms represented by the formula Fe3PO4 So the key thing here is to reach back into your math brain and apply. So usually everybody says, all right, well, there's three Fe's, and that is true. And oftentimes people will say there's 8 oxygens, which is also true, but sometimes we forget to distribute this 2 here. So there's also 2 phosphorus. So 8 and 2 and 3 for a total of 13 total atoms represented in that particular molecule. Symbol that indicates a substance is dissolved in water. That I would hope. This is the symbol. And it's standing for aqueous. So aqueous compounds are ones that are dissolved in water. We don't have to take into account the oxygen or the water in the reaction. We're kind of assuming that it's there. What it's really meaning is, is that water is not really a player. It's not really involved in the actual chemical reaction, but that the chemical reaction wouldn't happen unless the components were in water. So if we're thinking about ionic compounds, oftentimes we talk about the fact that all of their exciting properties, or a lot of their exciting properties, occur in water. So a lot of our ionic compounds, when they're involved in chemical reactions, are going to be in the aqueous form. 2 white powders are mixed in a flask. The bottom of the flask feels cooler. This is an example of what kind of reaction. So again, you have to think about what that cool means. When it's hot, you guys have seemingly no problem saying heat is leaving the system, right? And that's very easy for us. Heat is exiting the system. Exit. We do sort of have an issue with entering and understanding cooler as entering the system. So if I have my flask, if the reaction is converting ETH to ECH, right, then in order to get my ETH back up to where it needs to be, it needs to pull in thermal energy from the environment, okay? You feel cold, right? It's pulling that thermal energy from you to into the reaction. But the other thing is that, like, it could still be doing it if it was just the environment, because room temperature is still a source of thermal energy. So that is the endothermic reaction. Again, remembering that it's entering. Endothermic reactions, thermal energy is entering the system. Exothermic energy is exiting the system. Remember within endothermic that there's really 2 options. You have option 1, which is you have your reactants and you have to add heating in order to make the reaction go. Okay, but on the flip side, so you're adding something to the system in that one. So that was like the baking soda, the sodium bicarbonate over the flame, right? You're adding something to the reaction in order to allow the process to happen. In other things like the hand packs, the cool packs, just the reaction itself is going to occur instantaneously, and then in order to get that thermal energy back up, energy is still entering the system, but it's after the reaction has already started to progress. Okay, so that feeling cold is because thermal energy is being converted into chemical energy, And then at the end, the thermal energy is trying to get back to that baseline amount of energy. What is the charge in PbSO4? This is a super simple one. If you know your polyatomics, you know this. You know that SO4 has a charge of -2, and since there's one Pb to one SO4, you know that the charge of lead in this situation has to be +2. I'm gonna, I guess you could do this. So use the following diagram to answer. So we have A, B, C, and D. What else must be going on? So if I have an A accounted for on both sides, one C accounted for, one B accounted for, and one D accounted for, what's left over here would be some sort of C, B, D. This is really getting at the law of conservation of matter. You have to make sure that you have the right number of atoms on both sides. I don't particularly love this question because it's unlike any that we've really ever seen, but if you're talking about it in terms of making law of conservation, what are the particles on the left? They're the reactants. What are the particles on the right? They're the products. The arrow means that a reaction is occurring. Those are the important things from that section. So this is kind of on you, but here's what I'm going to say. We did a whole lab where we looked at all sorts of different chemical reactions, and there's some things that you guys saw. You guys saw that that gases were produced. You saw that colors changed. You saw that fire happened. You saw precipitates form, right? Where you had, this was always my favorite, and nobody seems to be as excited, where you have two solutions of liquid. They're both clear, and you mix them together, and in this you get this like foggy, cloudy precipitate that forms. So you've not only have you changed colors, you've also changed state of matters. You've gone from liquid to a solid, and again, that's that double displacement. Two things are switching sort of partners, right? Your anions and cations, and they're giving you something completely new. Again, that completely new is incredibly important when we're discussing chemical reactions. Balance the reaction. Okay, well, sure, why not? This is one that people don't always like because they think that the issue is on the product side. But let's just take a look here. And let's count our atoms. A, B, C, and D. A, B, C, and D. Here we have 1A. Here we have 1A. Here we have 3 B's. Here we have 3 B's. Here we have 2 C's. Here we have 1 C. And here we have 4 D's. And here we have 1 D. So what must be the other thing, and which side must it be on? I simply have more atoms on this side. So it's clearly over here. My discrepancy of C is 1. So I need to account for 1 more C. And I need to account 1 and 4. I need to account for 3 of the D atoms. Okay, so there, now I've balanced my equation. So how would I write this? I would say dB2 plus, let's see, CD3 plus BAC becomes C2D4 and AB3, all happily balanced. I hope I don't have to go over reactants and products again. This one trips people up, and I think it's just a totally different way of looking at everything we've been looking at in terms of atoms rearranging. But again, it's okay. It's not that big of a deal. If you start with the law of conservation of mass and you end with the law of conservation of mass, you're going to be in pretty good shape. Okay, joy to the balancing. So the next two things here is really where I'm going to spend the meat of the time. If you want to watch the other videos, I go through